Hello everybody, today we start with one of the most important chapter of chemistry, that is stoichiometry. The chapter stoichiometry is divided into, I would say, 5 parts. So if you see, it is basically related to quantitative analysis of the chemistry. If you remember in the analytical chemistry part, I told you that the analysis is divided into 2 parts, that is qualitative and quantitative. In qualitative, it is telling us that what is the kind of elements present, or what is the type of cations and anions present in the compound. So that is the analysis which is qualitative analysis. But in case of stoichiometry, what we will be having is the quantitative analysis. That means it is going to quantify the amount of compounds, or it is going to quantify the amount of cations present in a compound, or it will quantify that what is the resultant amount of some product formed, right? So when we are talking about the quantity, when we are talking about how much amount of the carbon is going to be required, how much amount of carbon dioxide is produced, how much amount of oxygen is going to be required, so whenever we are trying to find out the quantity of any particular compound required or is going to be obtained in a particular reaction, we call it as the quantitative analysis, which is going to be studied under the heading of stoichiometry. Now, as I told you, the stoichiometry can be divided into 5 types. That is, there will be 5 different kinds of questions related to stoichiometry. The first one is the one which is connected to the Gay-Lussac's law. There is a law which is called as the Gay-Lussac's law and Avogadro's law. So Gay-Lussac's law and Avogadro's law makes the first part of the chapter, chapter, yeah, that's right. And then there will be the next one which is going to give you the explanation about the Avogadro's principle, that is nothing but the amount equations जो रहते हैं उसके बाद, तो that will be Avogadro's principle. And then we'll be having something related to the vapor density and the molecular masses and the percentage composition. So when you're talking about the percentage composition and molecular mass and all, that will be the next part of the chapter that will be related to that. And then will be a mole concept. So we will be having something related to the mole concept. What is a mole and how we are calculating the mole, or what is the different relationship between the mole and the grams of a particular atom. There will be mole concept, and finally will be the chemical equations to find out the amount of compound required or formed during any reaction. So this way you are going to have the 5 different kind of questions over here. Now what we are going to now in this chapter, if you see the chapter in a whole, you will find that it is divided into 2 parts. पर हम लोग क्या करेंगे, हम लोग एक पार्ट पढ़ेंगे और उसके रिलेटेड के न्यूमेरिकल्स करेंगे, उसके बाद सेकंड पार्ट पढ़ेंगे और उसके न्यूमेरिकल्स करेंगे, सो दैट यू आर अवेयर अबाउट द टॉपिक एंड यू आर हैव ए कंटिन्यूटी अबाउट द टॉपिक. आई डोंट वांट यू टू लर्न ऑल द कॉन्सेप्ट फर्स्ट एंड देन डू ऑल द न्यूमेरिकल्स एट द सेम टाइम. ऐसा करके फायदा नहीं है. We'll go piecemeal basis. So first of all, we'll understand this chapter and from the first point of view, first category, that is the Gay-Lussac's law, and then we'll solve the answers, numericals for the same. But before we start, we need to understand one major thing, and that is all the concept of mole concept or stoichiometry which is there is related to gases. This is because the gases are the only one which are going to be having different volumes at different pressure and temperature conditions. We had studied the gas laws in the 9th standard. So we see in the gas laws that if the pressure increases, then the volume decreases, and if the temperature increases, the volume increases. So if due to the change in temperature and pressure, the gas is going to be either increasing or decreasing in pressure, decreasing in volume. So accordingly you will find that gases के अंदर ही मुझे ये सब जो भी calculation करना है, that will be related to gases, except for the mole part. The other parts will require to be in terms of gases. Okay, so that is there, that whatever reaction I'm taking, if I'm taking any reaction in Gay-Lussac's law, I'll be taking only those reactions which are in terms of gases. Those which are already solids or liquids, I cannot take the ratios of that. So that will just keep this in mind. Of course, when we do the sum, I'll explain you once again, but right now just keep it in mind that it is all related to gases. So introduction wise, gases have no definite volume and shape and no rigidity. The intermolecular space between particles is maximum and the force of attraction between particles is negligible. Where solids, the solid has definite volume and shape and are highly rigid. Intermolecular space between particles is minimum and the force of attraction between particles is maximum. Whereas in liquids have a definite volume but no definite shape and are less rigid, and intermolecular space between particles is more than solids, but the force of attraction between particles is less than solids. So this was a general thing about these gases, liquids and solids. The second is gases exert pressure on the walls of the container. Solids exert pressure only partially downwards, whereas liquid pressure exerts pressure only partially downwards. Gases generally have low density, least number of particles per unit area. Solids have generally high density, more number of particles per unit area, and liquids have density less than solids, less number of particles per unit area. Gases have high miscibility. They can get mixed up together very easily. So gases are highly miscible. Particles rapidly diffuse with the particles of other gases. Solids have been seen have no miscibility. Solids do not get miscible. They are not mixed up. Particles do not diffuse with the particles of another solids. And liquids have a slight miscibility. Particles may diffuse with particles of another liquids. Accordingly, we see the gas law. We are just going to take a quick recap of the gas laws which we studied in the 9th standard. So gas laws are certain rules which gas follows when subject to the change in temperature, pressure and volume. So when any particular gas is subjected to a change in temperature, pressure or volume, you are going to get a resultant over here. So that is nothing but the resultant is going to be identified by the gas laws. So the effect of change of any one of the parameters, that is temperature, pressure and volume, affects the other two parameters. Temperature an indicator of the average kinetic energy possessed by the molecule. Units is Celsius, degree Celsius or Kelvin, and 0 degree Celsius is 0 plus 273 Kelvin. Pressure, average force exerted by the gas molecules on the walls of the unit area. So whatever the pressure exerted by the walls, that is nothing but the average force exerted by on the walls of the container, that is the pressure. And it is measured in atmospheric pressure, or it will 76 centimeters or 760 mm of Hg. Volume, space occupied by the fixed mass of gas, that is the amount of volume which is going to be there. It could be in liters or cubic centimeters, that is 1 liter is equals to 1 dm cube or 1000 centimeter cube or 1000 ml. Now study of the relationship between pressure and volume of a gas. There is temperature constant and temperature and volume of a gas when pressure constant. That is nothing but Boyle's law and Charles' law. So summarizing the law studied, Boyle's law, temperature remaining constant, the volume of a given mass of a dry gas is inversely proportional to the pressure. Its pressure, that is V, is that inversely proportional to 1 upon P, where T is constant. So this is nothing but Boyle's law. So Boyle's law is the first thing we have. Boyle's law is that temperature remaining constant, then the volume is inversely proportional to the pressure. Okay, volume is inversely proportional to the pressure. More the pressure, less the volume, lesser the pressure, more the volume. Second is Charles' law. So that is the Charles' law now. Of course, we have studied this thing, so not a problem. There is pressure remaining constant. And in this case, what happens? It is seen that Pressure remaining constant, the volume of a given mass of dry gas is directly proportional to its absolute temperature in Kelvin scale. So that is why we see that volume is directly proportional to the temperature, but that temperature will be in Kelvin scale only. It cannot be in degree Celsius. So that's why we get P is directly proportional. And according to applying this thing together, we have the gas equation. So the gas equation which we got is P1 V1 upon T1 is equals to P2 V2 upon T2 is equals to K. So that is P1 V1 upon T1, that is the gas equation, as P1 V1 upon T1 is equals to P2 V2 upon T2 is equals to K, that is constant. And volumes of gases are converted to standard temperature and pressure conditions, and they then compared. So always whenever you are going to take any particular volume of a particular thing, gas, you will always convert that into STP. What is STP? Standard temperature and pressure condition. What is the standard temperature and pressure conditions? STP का values जो है, STP is temperature is equals to 0 degree Celsius 273 Kelvin and pressure is equals to 76 centimeter of Hg. That is 1 atmosphere, that is the pressure, which is nothing but the standard temperature and pressure condition. So volume of gases change with temperature and pressure. Hence, a standard value of temperature and pressure is chosen to which gas volumes are referred. The standard temperature and pressure values are standard temperature 0 degree Celsius 273 Kelvin and standard pressure is 760 mm of Hg or 76 centimeter of Hg or 1 atmospheric pressure. So this is what we had already studied in the 9th standard, that is given as the Boyle's law, Charles' law and the gas equation in STP. Okay, so now we start with the new thing which is there in stoichiometry. We start with the first thing, and that is called as Gay-Lussac's law. So first thing what we have is Gay-Lussac's So first small history. In 1801, Boyle and Charles have proved the gas laws showing that equal volumes of all gases behave similarly under similar conditions of temperature and pressure is systematically changed. In 1800, John Dalton, in his atomic theory of matter, stated that the smallest indivisible particle of matter in the atom is the atom which takes part in a chemical reaction forming molecules or compound atoms. When atoms combine, they do so in numbers which bear a simple whole number ratios to one another. So this was the two basics. One was Boyle's law and Charles' law, that the volume of a particular gas is going to be directly dependent on the amount of pressure and temperature conditions prevailing on that particular gas. This was first part. And at the same time, in the same region, John Dalton suggested that all the elements are made up of atoms, which is the smallest particle, and when they do react, so whenever the atoms react, they are going to react in a simple whole number ratios with each other. So these two things, the two things, that is the thing given by the Boyle's law and Charles' law and the one which is given by John Dalton, was studied thoroughly by Lussac, and he gave his findings, and that is in 1805, Lussac, on the basis of his experimental work, discovered a relationship between the combining volumes of gases used and products produced under the same condition of temperature and pressure. So he found that there was a relationship between the volumes of the products formed and the raw material, that is the reactants used. So there is a relationship, there was a direct relationship of the reactants and the products so formed in the same temperature and pressure conditions. In 1811, Amedeo Avogadro was able to explain Boyle's law and Charles' law on basis of equal volumes of all gases under the same pressure of temperature and pressure equal number of molecules. He further proposed Avogadro's law, which helped in correcting Dalton's atomic theory. So Avogadro was a person who identified that if I have equal volumes of certain gases, then if the volumes are the same, then the molecules present in them, okay, will also be same. For example, if I take a 1 liter bottle and I put like say hydrogen in it, I take another 1 liter bottle and put oxygen in it, both are now 1 liter. If the temperature and pressure conditions in both these particular bottles are the same, then the number of hydrogen molecules present in one bottle will be equal to the number of oxygen molecules present in the other bottle. So we can say that Avogadro stated that equal volumes of gases contain equal number of molecules in them. So that was what Avogadro gave, and this particular Avogadro's principle is very important as it gave us the explanation to Boyle's law and Charles' law, and also it gave some kind of correction to Dalton's atomic theory. Now we talk about the Gay-Lussac's law. Yeah, so Gay-Lussac's law, let's understand it. You need to learn this by heart. You are asked question as define or state the Gay-Lussac's law. So it's very important to learn it word to word because it's a law. Law, it is also called as law of combining volumes of gases. So it states, when gases react, they do so in volumes which bear a simple whole number ratios to one another and to the volumes of the products if gases, provided the temperature and pressure of the reacting gases and their products remains constant. What does it mean? It means that suppose I have got two gases. Okay, if I got two gases, these two gases, when they react, they are going to be reacting in simple whole number ratios. यानी क्या? इसका 2 volume तो इसका 3 volume, इसका 1 volume तो इसका 1 volume, इसका 2 volume तो इसका 5 volume. But it will be ratios will be in the form of whole number ratios with one another, and also इसका जो प्रोडक्ट समझो ये दो बना है तो ये दोनों का के साथ में इन दोनों का ratio with in dono will be in whole number ratio. So the reactants and the products, the gases which are reacting and the products of the gases which are being formed, they all will be under whole number ratio. They will be in whole number ratios provided that this reactants and products both are in the same temperature and pressure conditions. If the temperature and pressure conditions for the reactants and the products is the same, only then you can see that this particular thing is going to hold good. So that's why we can just read it out once again, that when gases react, so I told you, when gases react, they do so in volumes which bear a simple whole number ratios to one another and to the volumes of the product, okay, and to the volumes of the products if gaseous, okay, only if it is gaseous, provided the temperature and pressure of the reacting gases and their products remain constant. Lussac's law can be verified or illustrated by studying the following example in which a simple whole number ratio exists between the gaseous reactants and products. So what is the thing what we are talking about is this way, that if we take over here, like let's say we know that H2 plus O2 is going to give me H2O. Now if this H2O what's so formed is in the gaseous form, that is in the water vapor, then I know that I need to balance this thing. And to balance it, I have to put 2 over here, 1 over here and 2 over here. That means that the ratio in which the two gases are reacting and the products are formed is in the ratio 2:1:2. This is nothing but as per Gay-Lussac's law, that the ratio of the reactants and with the products is going to be whole number ratio. So whenever the reactants react, whenever the two gases react, they are going to do so in simple whole number ratios, and also will be simple whole number ratio with the products so formed if gaseous. Same thing, we can also have another example over here where we are taking nitrogen N2 plus H2 giving me NH3. So you can see over here the reaction will be N2 plus 3H2 to give me 2NH3. So again the ratio will be 1:3:2. So this is the Gay-Lussac's law. So one volume means any particular volume at a given pressure and temperature. So one volume over here, it's possible that if I take over here, this is one volume. So if I take 10 liters, so this will be 30 liters and this will be 20 liters. Like I take over here as 20 liters, then this will be 10 liters and this will be 20 liters. So 20 liters of hydrogen reacting with 10 liters of oxygen will give me 20 liters of water vapor at the same temperature and pressure conditions. Similarly, 10 liters of nitrogen, or let's say 5 liters. 5 liters of nitrogen with 15 liters of hydrogen is going to give me 10 liters of ammonia gas. Got it? So here we can say that this ratio here, so automatically we will be having a whole multiplication factor. So automatically if I take it as x, so that is x is what we are going to connect to. So here in the example of 5 liters, x is 5. So it will be 5, 15, 10. Here if I take 10, then it's 20, 10, 20. Okay, where x is 10. So this is the kind of questions they are going to ask you in the numericals. So you can see the numericals are going to be very easy, because numericals में सबसे important काम क्या होगा? Balancing the equation. If you know the balancing of equation, you automatically have found out the ratio, and then it is just that इसको इतना तो कितने को कितना. Okay, that is simple unitary method. Okay, so now what we'll do is that I'm going to take one see, there are around 9 solved examples over here, and then there is on page number 85, there are additional problems. There are 8 problems based on Lussac's law. So what I'll do is that I am going to do the first sum and the 9th sum of the solved example first for your understanding, and then we'll take up the 8 sums which are there in the exercise, the additional question. So additional question may say we are going to do that way. So first of all, let us understand the first 2 questions, first and the 9th question of the solved example. So we have the first question as 450 centimeter cube of carbon monoxide and 200 centimeter cube of oxygen are mixed together and ignited. So they are saying that now first of all, it is quite possible that they will not give you an equation over here. They are just given you the reaction. You have to frame the equation. So you have, like for example in this case, they are not given you the equation. So we have to frame the equation that we have taken CO and we are reacting with O2 to give me the resultant will be of course compound, which will be CO2. So mixed together ignited, so of course we are going to get CO2. Now we need to balance this. So to balance this thing, this is already equal, so this is 2 and then it will become over here as 2C to 2CO, and that is 2 before, so this is 4, yeah, that's it. So 2CO plus O2 gives me 2CO2. This is the required equation. Now you can see, so the ratio over here is 2 is to 1 is to 2. They are given us that this is 450 centimeter cube. This is 200 centimeter cube. And you need to find out that what will be the composition of the resulting mixture. Now you can see that if I take this to be 2x is 450, then x will be 225, but I do not have that much amount of oxygen with me. See, it's very important which you have to take the base. the base will be something which is lesser in quantity, because if you are taking something which is more in quantity, then here you do not have sufficient oxygen to form that much carbon dioxide. So it will happen that here you are going to utilize this completely, and this is going to remain balanced, and this is what you are going to obtain. So here you see that we will take that this to be as the base. So here this is the base. So if I take this as the base, we take over here x is equals to 200 centimeter cube. Okay, so if x is equal to 200 centimeter cube, automatically 2x will be how much? Therefore 2x will be equal to 400 centimeter cube. See, this is 2x, this is x, and this is 2x. So now you know that CO used is equals to 400 centimeter cube, CO2 formed is equals to 400 centimeter cube. But what is the resultant mixture? Resultant mixture will be such that O2 is used completely, but CO will be partly used. So CO balance is equals to 450 minus 400 is equals to 50 centimeter cube. Got it? So what is the resultant? Result, CO remaining is equals to 50 centimeter cube, CO2 formed is equals to 400 centimeter cube, and oxygen used fully. Understood? So resultant mixture will be equal to 450 centimeter cube of a combination of the two. Okay, that is unused CO 50 and CO2 formed 400. This is how you are going to find out. Very simple. It is just one main important thing, and that is what you take x. Whether you take this as 2x का लिए x लेंगे या इसको x लेंगे. Okay, so if you take this as x, then x is equal to 200, then 2x will be equal to 400. So here 2x should be 400, but you have got 450 instead of 400. So automatically you have got 50 balance over here. Samjha? Good. Now we see the ninth sum. A mixture of 10 centimeter cube of CO, 60 centimeter cube of H2, and 25 centimeter cube of CH4, that is methane, are mixed in 750 centimeter cube of air containing 20% oxygen. So here you can see there are three equations we are going to have. The first equation is CO plus O2 giving me CO2. The second equation will be, you are having the hydrogen, so that is H2 plus 2H2 plus O2 giving me 2H2O. And the third thing what we are having is CH4 plus O2 giving me CO2 plus H2O. Okay, so balancing this thing, so C plus 2H2. So the ratio over here is 2 is to 1 is to 2. Here it is 2 is to 1 is to 2. Here it is 1 is to 2 is to 1 is to 2. Right? But I will not take this because this is a liquid. So we will take only this part. Okay. Now we have got over here 750 centimeter cube of air with 20% oxygen in it. Okay, so 750 centimeter cube of air, therefore O2 is equal to 20% of 750. That's 150 centimeter cube of O2. So for all the reactions 1, 2 and 3, the total oxygen what I have got is 150 centimeter cube. Now let's see what are the things they have given us. So they are given over here, this is 10 centimeter cube. The hydrogen is 60 centimeter cube. And the methane is 25 centimeter cube. Sorry. So in this case, if this is 2x is equals to 10, therefore x is equals to 5, therefore O2 required will be equal to 5 centimeter cube, right? And CO2 formed is equals to 10 centimeter cube. So this is the resultant of this reaction. The resultant of reaction will be O2 used up is 5 centimeter cube and CO2 formed is 10 centimeter cube. Now let's take this one. You have got 60 centimeter cube. So therefore 2y is equals to 60. Therefore y is equals to 30. Therefore O2 used is equals to 30 centimeter cube and H2O formed. Now this could be water also, so we'll not worry about it. So we take this as water, that is liquid, so we'll not worry at all. So we will not see this at all. Okay, because they say that yes, the important part over here was the last sentence of the question. Calculate the composition of the resultant mixture on cooling to room temperature. So on cooling to room temperature, this H2O and this H2O becomes liquid in nature. So this being liquid in nature, that's why we cannot use Gay-Lussac's law. Got it? So what is the resultant over here? The resultant is that I am using up this much amount of oxygen over here. We come to this part. We see over here the 25. So let's take Z is equals to 25 centimeter cube. Therefore 2Z is equals to 50 centimeter cube. That is O2 required is equals to 50 centimeter cube and CO2 formed is equals to 25 centimeter cube because it's just one. Got it? So what we see, the total oxygen required. So total O2 used is equals to 5 over here plus 30 plus 50. So it's 5 plus 30 plus 50 is equals to 85 centimeter cube. Therefore unused O2 is equals to 150 minus 85, that is going to give me as 65 centimeter cube. Got it? So O2, which is going to be unused. See, we are asked us that calculate the composition of the resultant. So in the resultant, I am going to have this as the first thing. That the first thing what is going to be the result will be this one. That O2, which is going to be unused, will be 65. Secondly, will be I am getting water over here. So water we are not considering. We are going to consider the other part, that is the, see, methane got used up, hydrogen got used up, carbon monoxide got used up, CO2 is formed. CO2 formed over here is, CO2 formed is equals to, you can see CO2 formed over here is 10 and over here CO2 formed is 25. So 10 plus 25 is equals to 35 centimeter cube. So resultant mein, first thing is oxygen, second thing is carbon dioxide, 35 centimeter cube. Now apart from that, you can see that in the air, if I say that I am going to utilize only oxygen and the other parts are not going to be utilized, so that becomes a part and parcel of the resultant balance. So what is the resultant balance? Of course, the rest of the part is nitrogen and other gases. So that's why we consider the other gases are how much? 750 minus 150 is 600. So nitrogen and other gases in air is equals to 600 centimeter cube. You can also put only nitrogen, other gases छोड़ो. सिर्फ nitrogen भी लिखेंगे तो भी चलेगा. Okay. So we see that the resultant of the composition will be carbon monoxide 0, hydrogen 0, methane 0, oxygen 65 remaining, carbon dioxide 35 produced, and balance nitrogen as 600 centimeter cube. Did you understand this? Okay, very important part. So this was about the thing. Now in the next video I'll solve the 8 questions which are there in the additional questions.